Laser surgery. Very short pulses of high-intensity laser beams are used to repair detached portions of the retina of the eye. The brief pulses of energy absorbed by the retina weld the detached portions back into place. So we have a complete absorption. In one such procedure, a laser beam has a wavelength of lambda equals 810 nanometers and delivers a power 250 milliwatts spread over a circular spot with diameter d is equal to 510 micrometers. The vitreous humor, the transparent fluid that fills most of the eye, has an index of refraction n of 1.34. Part A. If the laser pulses are each delta t is equal to 1.5 milliseconds long, how much energy is delivered to the retina with each pulse? Okay, so we know that the power delivered, P, is equal to the energy delivered per unit time. So it is E divided by delta t. Therefore, the energy delivered to the eye is simply the product of the power and the length of the pulses. So if we plug in the numbers here, the energy E is equal to 250 milliwatts, so 250 times 10 to minus 3 joules per second, multiplied by 1.5 milliseconds, that's the duration of each pulse. This gives us a total energy delivered to be 375 microjoules. All right, let's move on to part B. What average pressure, P bar, would the pulse of the laser beam exert at normal incidence on a surface in air if the beam is fully absorbed? So we know that the beam is fully absorbed by the vitreous humor. Okay, now what is the momentum transported by an electromagnetic wave? It's the energy carried by the wave, energy in electromagnetic radiation, divided by the speed of light. So the time derivative of the momentum is the force. So pressure is force per area. Therefore, what I need here is time derivative of the energy dT dt divided by the speed of light. So that gives me the dp dt, time rate of change of momentum, per perpendicular cross-sectional area gives me the pressure. Now we're talking about average quantities here. So this is basically energy delivered per unit time. That's power per area, which is intensity. So this is the average intensity divided by the speed of light. And we know that the average intensity is simply the average value of the magnitude of the Poynting vector, and we have to divide it by the speed of light. Now, what is the perpendicular area for this beam? It is pi times the radius squared, which is the diameter divided by 2 squared. Therefore, the average intensity is the average power delivered divided by pi d over 2 squared. From this, we can calculate the average pressure being exerted. average pressure being exerted is the average power divided by the area pi d over 2 squared times the speed of light. That's the average pressure that's being exerted. So if I plug in the numbers here for this average pressure, we have 250 milliwatts of power, 250 times 10 to minus 3 watts. Pi d over 2 squared is pi 510 10 to minus 6 over 2 squared, and then we have the speed of light 3 times 10 to 8 meters per second. So this is going to give us the value of the average pressure that is being exerted. So let's check that the diameter was 510 micrometers indeed. Okay, so this gives us an average pressure of 4.08 times 10 to minus 3 pascals. Now, it's very important that it's mentioned in the problem the absorption is complete. So if you have complete absorption, it's the average intensity divided by the speed of light. That's the pressure being exerted. That is for the case of complete absorption. And remember that if we have full reflection, then the average pressure being exerted will be twice the intensity, twice I average divided by C. This is the case of full reflection. So in this case we have complete absorption, therefore we don't need to worry about this factor of 2. Let's move on to part C. What are the wavelength and frequency of the laser light inside the vitreous humor of the eye? When light enters a medium with index of refraction n, its wavelength decreases by a factor of n. So lambda prime is lambda divided by n. And from this we can calculate the wavelength 810 nanometers, 10 to minus 9 in air, divided by the index of refraction of the vitreous humor, 1.34. So this gives us a wavelength of 604 nanometers. Okay. And what happens to the speed of light in this medium? The speed of light is also reduced by a factor of index of refraction. Index of refraction is by definition equal to the speed of light in air divided by the speed of light in the medium, remember. And that's because this is equal to the reduced wavelength lambda over n multiplied by the frequency in the medium. So from this equation you can see that the frequency in the medium is identical to the frequency in air because the frequency is determined by the source, not by the medium. So it is c divided by lambda. So we have the speed of light in air 3 times 10 to 8 meters per second divided by 810 times 10 to minus 9 meters. This gives us the frequency f prime 3.70 times 10 to 14 hertz. So the frequency is simply equal to C over lambda. So let's note here that the frequency in air is equal to the frequency in the medium because the frequency is determined by the source. The medium has no effect on the frequency of the light. Part D, what are the maximum values of the electric and magnetic fields in the laser beam? So remember that the average intensity is simply the average value of the time average value of the pointing vector magnitude, which is the time average value of 1 over mu0 E times B for a plane electromagnetic wave, and E is related to B. E is equal to B times C, that we find from Maxwell's equations. So this gives us average value of B squared C divided by mu0, the permeability of free space. And we have shown that the time average value of B squared is the amplitude B max squared divided by 2, and then we have C over mu0. So from this equation, we can determine what B max is. B max is equal to 2 mu0 over C multiplied by the average intensity, all inside the square root. All right, so we can plug in the numbers here. This is equal to 2 times permeability of free space is 4 pi 10 to minus 7. The intensity divided by the speed of light, 3 times 10 to 8. And for the intensity, we have 250 milliwatts, so 250 10 to minus 3 watts, divided by pi d over 2 squared, which is 510 times 10 to minus 6 over 2 squared, and this all inside the square root. Okay, so we obtain a maximum magnetic field of 1.01 times 10 to minus 4 Tesla from this calculation. And for Emax, all I have to do is multiply Bmax by C. So maximum electric field is Bmax times the speed of light, 3 times 10 to 8. So this gives us a maximum electric field 3.03 times 10 to 4 volts per meter. All right, so that answers part D of the problem. So we're talking about pulses of light, laser beam, with wavelength 810 nanometers, delivering 250 milliwatts power spread over a circular spot 510 micrometers in diameter, and pulse length is 1.5 milliseconds. Multiplying the pulse length with the power, which is energy delivered per unit time, we obtain the energy delivered to the retina with each pulse, which is 375 microjoules. What is the momentum, what is the pressure exerted by each laser pulse at normal incidence? The momentum transported is the energy carried divided by the speed of light. The pressure is dp dt, time derivative of the momentum, divided by the area, so dt er dt, divided by c multiplied by area A, perpendicular area A. This is simply the energy delivered per unit time, power, average power, divided by the area, which is the intensity, divided by the speed of light. And average intensity is the average value of the Poynting vector magnitude. So we can calculate the pressure as P average, the average power delivered, divided by pi d over 2 parentheses squared times C. So plugging in the numbers, we obtain the pressure to be 4.08 10 to minus 3 pascals. One thing to be careful about here is this wording, complete absorption. The pressure exerted is I average over C if we have complete absorption. If we have full reflection, then the change in the momentum will be twice the 2 TER over C, which means the pressure will be twice of this value, so 2I average over C. So that's what we need to pay attention to. The wavelength decreases by a factor of index of refraction. The speed of light decreases by a factor of 1 over n. And from this, we can see the frequency doesn't change because V is equal to lambda times frequency. The frequency is determined by the source, so frequency of the light is c over lambda, but the wavelength is lambda divided by the index of refraction in the vitreous humor. What is the maximum electric field and magnetic field magnitude? Looking at the average intensity here, average value of S, we realize that the Poynting vector is 1 over mu 0 E cross B for a plane electromagnetic wave. This is 1 over mu 0 EB, and E is equal to B times C from Maxwell's equations, where C is equal to 1 over square root mu 0 epsilon 0. So time average value of B squared is B max squared over 2 times C over mu 0. From this we can obtain the maximum magnetic field magnitude, and we can obtain the amplitude of the electric field by multiplying B max with C, and this is going to be our final answer.